we are on to an application of implicit differentiation. And that application is called logarithmic differentiation. And before we actually figure out what logarithmic differentiation is, let's see where it's going to be helpful to us. One of the places is if we have a function that has maybe multiple products, quotients, or maybe functions raised to powers. So in other words, it would be a mess of maybe the product rule, quotient rule, and maybe another product rule in there. Okay. And here's an example. Y equals tangent squared of x times the cube root of 7x plus 1 all over 4x squared plus 3, and this is to the 3 halves. Okay. Here, logarithmic differentiation will make this problem much easier. Okay. Now, that being said, you don't have to use it in case 1, it just makes things easier. Case 2, though, we're not really going to have any way around this. And let me explain why we don't have any way around this. We know how to differentiate some constant to the x, right? And we know how to differentiate x to some constant, right? That'd be using the power rule. But the question is, well, what happens when we have things with x to things with x? Okay. Well, we're going to use logarithmic differentiation. Okay. And actually, logarithmic differentiation could be used, it's not necessary, but could be used to differentiate things that look like these two. All right, so let's write down an example function. How about we'll call it h. So h of x is equal to, and let's go with cosine of x to the natural log of x. Okay, this would be one where we'd want to use logarithmic differentiation. Let's take a look at our procedure here. So this is what we'll do when we have a logarithmic differentiation problem. We'll take the natural log of both sides of the equation. Technically, you could use a log of any base, but we all have the natural log on our calculators, so this is a good choice. Okay. Now, the thing is after you take the natural log of both sides, you need to know your log properties. So if we have the natural log of a product, we can rewrite the natural log of xy as the natural log of x plus the natural log of y. If we have a quotient, okay, the natural log of x over y is equal to the natural log of x minus the natural log of y. And lastly, if you have the natural log of x to the r, that's equivalent to r times the natural log of x. Okay. And so we'll use these properties, and the reason that they're helpful is if we turn products into sums, then we don't have to use the product rule. And if we turned quotients into differences, we don't have to use the quotient rule. And the last one, sometimes it can make it a little bit easier to apply the chain rule. Okay. And after you've done all that, your equation is going to look a lot longer, but now when you perform implicit differentiation, the derivatives will be easier to take. And the last step will be to solve for y prime, just like in all our other implicit differentiation problems. All right, and so we have a great example to start with here. Y equals x to the x. And we're going to start off by taking the natural log of each side. Okay. Now we also have a log property that says if you have the natural log of something to a power, you can bring that power out front. Now that we've applied that log property, we're going to use implicit differentiation. So the derivative of the natural log of y, and I should point out we're going to take that derivative with respect to x, and maybe I'll include that actually in this next step here. Let's write that. I'm going to take the derivative with respect to x So the derivative with respect to x of the natural log of y, that should be 1 over y. And don't forget, y is a function of x, so we need to apply the chain rule here, so times y prime. And then the derivative with respect to x of x not natural log of x is going to require the product rule. So the derivative of x is 1 times the natural log of x plus x times the derivative of the natural log of x, which is 1 over x. And it looks like I'm running out of room here. Let's go ahead and multiply both sides by y here. So we get y prime is equal to y times the natural log of x plus 1. Right? And we don't have to end this here. Let's move back up. Okay, so we know that y was equal to x to the x. So why don't we replace that y with x to the x? So we get y prime is equal to x to the x times the natural log of x plus 1. After the last example, you might be feeling ready to give this one a try. If you are, go ahead and pause it. If not, we'll go ahead and jump right into this one. All right, so first step, take the natural log of each side. So we have the natural log of f of t is equal to the natural log of sine of t to the natural log of t. And actually, I'm going to get rid of one of those sets of parentheses just so that this is a little bit easier to look at. There we go. Next, we'll actually apply the same log property we did last time. We'll bring down that natural log of t. So we have the natural log of f of t is equal to, and again, I'm going to bring down the exponent. So we get the natural log of t times the natural log of sine of t. Now we'll use that implicit differentiation. We have d dt of the natural log of f of t is equal to d dt of the natural log of t times the natural log of sine of t. Next, here we're going to start off by taking the derivative of the natural log of f of t. So we should get 1 over f of t, and then times the derivative of f of t. All right, so this will be what we're going to be solving for here momentarily. That's what we're trying to find. And this is equal to, and we're going to have to use the product rule. We have two functions of t here. So the derivative of the natural log of t is 1 over t times the natural log of sine t plus the natural log of t. And now we need to take the derivative of this natural log of sine of t. So it's going to be 1 over sine of t, and then times the derivative of that inside function, which is sine of t. So the derivative of sine of t is cosine of t. And we can keep going here. We can multiply both sides by f of t. And it is what we're going to have with the right hand side is then f of t times the, actually I'm going to write it as 1 over t natural log of sine of t plus, and cosine of t over sine of t is cotangent of t, so I'm just going to say natural log of t times cotangent of t. And one more thing, we know what f of t is equal to. Let's remind ourselves. It was equal to sine of t to the natural log of t. So we can write this a little bit cleaner. We have f prime of t is equal to sine of t to the natural log of t times 1 over t times the natural log of sine t plus the natural log of t cotangent of t.